Uh, sí. Should I get started? All right. So, okay, we're coming to the end of this particular journey. We'll see how far we really go. So let's remember quickly what we did yesterday. Basically, I went through an argument where we start from the physical objects we see, which are particles. We find it convenient to put that information into local fields, which then allows us to write things in terms of a Lagrangian, a local Lagrangian, such that it makes our lives easy to implement physical principles like, for instance, Lorentz invariance or invariance under other transformations, other symmetries. And the rule is very simple. We just have to, if we want the consequences of a symmetry to be to apply to this physics, we just have to construct the Lagrangian, which is invariant under that transformation. In particular, for instance, Lorentz invariant. So that with that language at hand, now we are ready to discuss a couple more ingredients that we need to talk about Higgs physics. And so that continues with the theme of symmetry. So let me start with an analogy, which is, although it is not perfect, it is a useful analogy to have in mind, okay? And perhaps some of you have seen this analogy before, but let me go over the main points slowly. So this is a completely different system. The case of let's say a ferromagnet or a system of spins, and that interact amongst themselves in such a way that the energy of that interaction energy is minimized when spins are aligned. Okay. So in that case, we know that the ground state of the system, the lowest energy state, looks something like this, where all the spins are aligned in the same direction. And so if you imagine a little physicist living inside this ferromagnet, this guy would see this, let's say this is three-dimensional, for example, right? It will be completely obvious that there is one direction in space that is definitely different from the other two directions, right? Okay, so this guy starts doing experiments, and probably for most of his life he just believes that that's the situation. One direction is special, right? He might at some point be able to build an experiment that is able to flip one of the spins, say like this, right? And so he discovers that he can do something kind of interesting to this world he's living in. But actually this, for him to or her to do this, it will require quite a bit of energy. Okay, so think of this as the analog of us today having built the LHC and being able to look at things at high energies. All right. So this is an excited state, and we can think of this as a high energy state. Now, actually, this is not the first thing this guy would have seen. Way before that, he would have seen other types of phenomena, which are illustrated here on the third line, which is also an excited state, means it's a state which has energy larger than this ground state. And so these are spin waves in which basically you take each of the spins and just give it a little kick, right? So it moves a little bit to one side, and then through the interactions that can propagate to others, and you can get interesting motions. For instance, here, as seen from above, we see that because there is let's say the z direction we choose as the one that aligned with the spins. There are two possible independent ways in which you can perturb the system, let's say in the x and y directions. So there are two spin modes that may look something like this. And these kind of perturbations, those do not require too much energy. So you can just give it a little kick, and then you will start seeing these things. And you can do this for arbitrarily small kicks, okay? And like this other situation where if you want to flip this guy here in the middle, you really have to give enough energy to compensate, right? Okay, so these kind of modes are interesting and would be, in fact, once perhaps this person has thought a bit and developed a bit of theory, he would call them Goldstone bosons, all right? And these he would describe as massless excitations, in the sense that you can excite them with arbitrarily small energy kicks, all right? So this is a low energy manifestation that this low energy being would be able to perceive, and actually, once he understands a bit more, he would be able to infer from those observations that there is something else going on here behind this thing, which is that the dynamics that is governing all of this actually does not have a preferred direction like we're seeing here. It is rotationally invariant, as we know, right? But nevertheless, in your ground state, you're pointing in some direction. Could have been a different direction, right? Okay, so this is the phenomenon that we call spontaneous symmetry breaking. It's the case where you have some dynamics, meaning a Lagrangian that describes the appropriate degrees of freedom, that is invariant under some transformation. There is a symmetry, but the ground state does not display that symmetry explicitly. It chooses one direction. The symmetry is still there, okay? So remember that the definition of a symmetry is just a statement about what happens to your theory, your Lagrangian, after you apply the transformation. And the way this is manifested here is that, yes, there is, your state may be this one which is pointing up, right? Ferromagnet pointing like this, but perhaps there is another world where the ferromagnet is pointing in some other direction, right? And both can be described by the same exact theory. And the physical properties of those situations are related by the symmetry. So those two things, ferromagnet in this direction or in that direction, they are really different physical states, okay? You could imagine with lots of efforts to transforming one into the other, for instance. They are different physical states whose properties are connected by the underlying symmetry, okay? And these Goldstone modes are a manifestation of this fact that the ground state doesn't like to display that symmetry explicitly. Make sense? Okay. So it turns out that the ground state, which we call vacuum, of our universe is somewhat like this, like a spin system like that, in the following sense. So first of all, the Lagrangian, so by our universe here, okay, I'm defining this to be the standard model Lagrangian, okay? There may be other physics that we don't know about, but our standard model Lagrangian describes a number of observed degrees of freedom. They interact with each other in complicated ways, but that displays a relatively high degree of symmetry. These are both space-time, but for our purposes here, more importantly, internal symmetries like the ones I illustrated on the previous lecture. Also, like the ferromagnet, turns out that the ground state has arbitrarily chosen a particular direction in field space, and thus is breaking, in quotation marks, the symmetry spontaneously, okay? For some reason, this is energetically favored, more or less in analogy to what happens in the ferromagnet example. Now, more precisely, one should really say that the symmetry is hidden rather than broken, because the symmetry as a symmetry in the technical way we define and with the consequences that this implies is still there. The Lagrangian is still the same. The statement that the Lagrangian is invariant under a certain symmetry transformation does not refer in any way to what is the ground state of the system. Okay, so those there are still conserved charges and so on. Interpretation may be a bit more subtle, but those things are there. Okay. Now there is an important difference between what's happening in our universe and the ferromagnet example, which is that in our case there is nothing analogous to the spin waves that I described before. Okay, these low energy modes that the little guy in there could have excited easily, and by thinking a little bit maybe discover that or more easily that the dynamics behind is actually rotationally invariant. So this small difference actually made it significantly harder for us to discover that these symmetries I'm talking about here were indeed there. Okay, and okay, so the purpose of the rest of the lecture is to explain this a bit more. So let's go back to the theory of the four scalar, four spin zero particles that I introduced last time. I wrote them as this capital H, which has two components, so it's a doublet. And now, so here I'm really, without apologies, I am interpreting this as the standard model Higgs doublet. Okay, this is how we parameterize it in the standard model. We also saw that the theory I wrote down yesterday had an SU2 cross U1 symmetry, which I am repeating here. So the SU2 corresponds to transformations where you multiply this doublet by these 2 times 2 matrices, where these taus are the Pauli matrices, right? So this is an SU2 transformation. And the U1 is basically multiplication by a phase. Yesterday, I was putting here some charge I call QH. I am choosing here QH equals 1/2, which is just a normalization, okay? So at this point, really you could choose anything, and in some formulas, at some point I will display QH, or sometimes 1/2. But what is really important is, so I can normalize this to 1/2, no loss of generality. But what will be important then is when I have several other fields, like for instance the fermions of last class, then the relative charges, those are the physical thing. Now the non-trivial observation, which is this spontaneous symmetry breaking, is that the ground state in our theory, in the universe, is something like this. I wrote it as 0V, where V takes a non-zero value. So this is something that points in a particular direction in this field space, okay? So whereas the Lagrangian is invariant in these transformations, which tells me that I could choose that direction in field space or that other, and it doesn't make a difference, and that is true, but the ground state has chosen a direction, and that's the statement that this V I have written here is non-zero. And it has this value, 174 GeV. We know that, we have known that for a long time. Now a small comment here is to note that I wrote this as 0V, and this is just a choice, an arbitrary choice of direction, totally analogous to saying that if my spin system is looking like this, I decide to call that direction the z-axis, okay? I just choose my coordinates to align them with the actual direction preferred by the magnet. So similarly here, this choice, which is a standard choice, there's nothing special about it. I can always do that, but the important thing is the statement that this is choosing some direction, a special direction in field space. So if the ground state, I'm telling you, because it's an experimental fact, that likes to do this, there is this V different from 0. If it's doing that, it must be that there is some potential, when I write my the Higgs part of the Lagrangian, there is some potential I'm calling V, okay? I'm writing this as V as a function of h dagger h to make sure that this will be invariant under this transformation I was talking about, because the matrices in between will cancel out, they being unitary. And this potential must have the property that at this value V, the first derivative vanishes, so this tells me this is the minimum, and that it's actually positive, so it's really a minimum as opposed to a maximum, okay? So this must be the case. Now, we really don't know a lot about, experimentally speaking, about what are the the detailed features of that potential. But one possible way to parameterize this, which will be useful to have something concrete in mind, is something like that. Let me write, so V of this, something like a coupling lambda, which we take as positive, times that. So we see that, so this is the famous picture, right? The wine bottle potential. This likes to, when you minimize, to have H, dagger H equals to V squared. And so this has here some direction, a flag direction, which just indicates the different possible choices in field space for this. But any of those I can choose any of those, okay? Although living in one is a different physical state in principle from living in another one, if we make the connection to the ferromagnet, okay? You could think that. So, okay, so let's, I will, for the following, you are welcome to imagine that we're using this particular potential here, although you will see that sometimes I will just write a generic potential, because most of the properties that I will be discussing actually do not depend on the specific details of that potential, only on the fact that it likes to have a minimum where your field is non-zero, is pointing in some direction, okay? So I will take this potential, if you want to have something concrete in mind, and I will choose this convention of putting the non-zero, so pointing in this direction, non-zero V in the second component. Now recall that if you think about the ferromagnet example, so things are say pointing in the Z direction. If I were to rotate the spin switch along the Z direction, that will not change that the fact that it's the Z direction which is special, okay? It's only if I make rotations along X or Y that I would change things. I would go to one of the other possible ground states. And in this case, it turns out that there is something analogous to that Z rotation that doesn't change your ground state. And I'm telling you here, so this is just to remind you, so these are the transformations that are in a symmetry of my Lagrangian. Theta, I'm calling the parameter for the U1. Theta I with I equals 1, 2, 3 is the one for the SU2. Wait. Sorry. So if I choose this particular transformation where I take theta equals to theta 3, so the tau 3 rotation, and the other two, theta 1 and theta 2 equal to 0, so that means I'm taking H to something like this, the U1 phase, and this particular SU2 transformation that I also discussed yesterday. And if we just plug in what this is, this looks like this. It has a 1 in this. So first of all, these are both are diagonal. And this entry, the 2, 2 entry, we see that because of this choice, and tau 3 is a 1/2 minus 1/2, so minus 1/2 in the 2, 2 entry, it cancels this one. So there is no phase here, and there is some phase here, e to the I theta. If I let this apply on this vacuum state 0V, that doesn't do anything. It leaves it the same. So this is the analog of the Z-axis in the ferromagnet case. This other component would transform according to this, e to the I theta. And if you apply other transformations that you can also consider, I will just tell you, this is something you can check, that all of those will rotate H non-trivially. So in the spin case, it's something like rotation in X or Y or some combination like that. Now it will be convenient, so that's the vacuum, okay, that's the ground state. But so this is step 0 to understand any problem, to understand what is your ground state, but after that you're interested in knowing what are the types of excitations that you can have. And for that it's useful to parameterize the 4 degrees of freedom that we know are described by H. Remember, these were 4 spin 0 particles, okay? And it is convenient to parameterize them in this particular way, okay? So the fact that, we have this V here, and the 4 degrees of freedom are put as follows. This little h, which is, so that you know already, this is the Higgs boson, which we discovered in 2012. And then there are these other 3 degrees of freedom, I'm calling them chi with vectors. So there's a chi 1, chi 2, chi 3. Each one goes with the tau matrix. And one exercise for you to check is that indeed this is these 4 degrees of freedom are independent. It's a fine way of parameterizing the 4 degrees of freedom I have to begin with, okay? In this notation of something in the upper component and something in the lower component, again, for notation so that, that you will see. Now, before I was calling them H1 and H2. Now, and it is standard, instead of calling them 1 and 2, we're putting a superscript, and that superscript indicates the charge under the unbroken U1. The unbroken U1 is exactly, if I can get there, no, oh. Is this transformation that doesn't change the direction of the vacuum. And we see that the 1, 1 component is being multiplied by e to the I theta. So if this guy was charge 1/2, this is, under this combination, this is charge 1, and this one is charge 0. E to the I 0 is 0. So this is just notation. So this plus and 0 refer to the charge under that particular U1 that doesn't change the direction of the vacuum state. Now, if I take the potential and I use this parameterization, so V is a function of h dagger h, you see that if we replace this exponential in front will cancel out between the h dagger and the h. So this will be just a function of V of this part, V plus h whole thing squared, okay? And so that's just a general feature from the fact that this depends on this combination. It is a function that is invariant under these transformations we are discussing. And if I choose this particular potential and expand, you will find 3 terms like this. There are, so let's look at these two. You see there is an h cubed and h to the 4th term. So those are trilinear and quartic interactions. So in the intuition we have been mentioning before, so this means that a Higgs boson or 2 Higgs bosons can scatter into a third, for instance. So there are vertices like that, and also involving 4 Higgs bosons. The first term, which is quadratic, okay, this is something we have seen before. This is what we call a mass term, okay? It's the piece that in the quadratic part of the Lagrangian that has something to do with defining the mass of the fluctuations. And so here we identify what the Higgs mass would be, and we see it depends on this quartic coupling lambda here, lambda, and also on V, the vacuum expectation value, the VEV. And it has this formula, okay? So there is a connection between mh squared, lambda, and v squared. Now notice that I told you before, we have known that V is 174 GeV, so it's 174 times larger than the proton mass, for a while, okay? We didn't know until recently, we didn't have any information about what lambda was, and we hadn't seen the Higgs. So this guy, we didn't know its value, okay? And this connected with our ignorance about lambda. But now that we have measured this, we can infer something about lambda from this term. I will get back to this point towards the end. These other 3 degrees of freedom, which are part of H, okay, the chi's, we see that they do not appear at all in this potential. That means in particular that there are no mass terms for them. If they are there, they are massless. Not only that, they don't have interactions between themselves, at least coming from a potential like this, okay? So actually these chi's, they would be the analog of the spin waves in the ferromagnet case. Except that in this case, as we're going to see, they are just a mirage, okay? They are not there. And so this is one of the things that, okay, we'll want to explain. So now we have to, we have to recall that nature has given us spin 1 fields, which I showed you yesterday, 2 examples, right? The Z and the W, these are spin 1 fields. You can do other measurements, and you can, or experimentalists and the community can get convinced that these are spin 1 fields. There are also things that are not spin 1, like this, the top quark, but there are these guys. And so if we recall the discussion yesterday, if you want to allow these spin 1 fields to interact with other things, it better be that they do so through conserved currents, okay? So in this case, because we have this SU2 cross U1 global symmetry, it means we do have conserved currents, and those are candidates to couple to perhaps these guys, okay? So let me, to exemplify how this proceeds, let me take the case of the U1 current. Remember, there are really 4 currents, one for the U1, 3 for the SU2, because there are 3 Pauli matrices, tau 1, tau 2, tau 3. Each of those defines an independent Noether current. But let me focus on the U1 only. So let's imagine that I'm trying to couple a spin 1 field to this Noether current. I'm going to call that spin 1 field here B mu. And pretty much by similar argument as what I run in the case of a QED, it's equation of motion, so we'll have a piece which is del mu B mu nu, and I want to put something on the right hand side which is a current, a 4 vector, which is conserved. And I want to build this because right now I am thinking about how these guys could and actually do couple to the Higgs. I want this J to be something constructed out of the Higgs field, the same way that when I was talking about QED, and I looked for a current made of the electron field in that case. And we can then try to do something similar to what we did there. So we can look for so what I am showing you here, J mu, this is the current connected to this U1. You may recognize, so I wrote a similar structure yesterday. In that case, it was for a tau 3 current, but this is very similar. And so this is indeed a current which is conserved. In this theory I have written before, for any potential here that is invariant under the U1 transformation in this case. So to get a term here on the right-hand side of the equation, it would be natural to try the same thing we did for the electron, right? We can write a term which is linear in our spin 1 field, B mu, and a coupling like this, B mu, J mu, because if we derive the equation of motion, this would put something like that on the right-hand side, all right? But here there is a small complication, which is that actually once you add this term, this expression I wrote here is actually not conserved in this full theory. Having added this term makes a difference, okay? And I don't have the time to go over the details, even though they are not complicated. It's algebra, okay? But you can check that in this full theory, this would not be conserved. And if you do that and see how it is failing, it also becomes obvious how to fix it, okay? So you can follow your nose, and what you will find is that if you modify your current by adding here this term on top of that one, a term that depends on 2 Higgses and a B, then, and in your Lagrangian, so I added here something complicated. The first term is actually what I had before. It was B mu times this J mu I had before, so I just expanded. That's why it looks complicated. But you can also add a term like that, okay? And one exercise for you is to check that indeed this thing here is the Noether current. So first of all, I should say perhaps that this, what I wrote here, is invariant under U1, which, remember, the U1 is a very simple thing. Just multiply by a phase, and basically we have always H dagger H everywhere, okay? So the phase cancels out. It's very simple. So there is another current associated to that. If you derive it in this theory, it will be this beast here, okay? So this is slightly, when you try to couple the spin 1 field to a scalar field like the Higgs, it turns out to be slightly more complicated than coupling a spin 1 field to a fermion field, as in QED. But conceptually, it's the same. We're just trying to make sure we are coupling, we're putting on this side of the equation something which is conserved. Remember that there is just an argument of consistency. It's also, again, I don't have the time to go over these things here, but it's very much connected to degrees of freedom, to having the correct, which means 2 degrees of freedom for this guy, okay? So let's take this Lagrangian, okay, that we have constructed. There's a question? Yes. No, let me. I don't. Let me. So the symmetry. Okay, the symmetry. I can just check that when I have, so let me put the explicit expression, right, even here. That term that was the leading term is this first term. My transformation is multiply h by e to the I theta over 2. Okay, we just check. H dagger h cancels the phase, here also. It is a symmetry, that's a fact. Then you have to work out the corresponding nodal current, right? I'm not, well, I know how, so that's the beauty of Noether's theorem, that gives me conserved currents, right? So I don't have to be too imaginative to derive them. I just follow a procedure. Yes. So it's a good exercise for you to try to do this exercise of, let's say, trial and error. And it's not difficult. You just see, and it will be more or less clear what you are led. So somebody is forcing you to write these things, okay? Just guided by the physics intuition or requirement that you really want here to have something which is really conserved in the full theory, okay? So you should be, you have to come to a point where the current you're writing here is really the current in the full theory, okay? All right, so we have this Lagrangian, so let's now use our diagrammatic representations to indicate clearly that now we have added really, so what we wanted at the end, we wanted this spin one field to interact, in this case, with the Higgs degrees of freedom. And we have added here terms which involve 1b, b mu, and 2 Higgses, which is this kind of vertex, or 2 Higgses and 2 b's, which is this kind of vertex, 2 Higgses and 2 b's, right? So we have added specific type of vertices. Also, the strength of each of these vertices, which we basically read from the coefficients, we see that there is a connection between both. Whereas this one goes like G1 QH, this one goes like the square of that, okay? And this is not optional, okay? This is enforced to us by the fact that we must couple the spin 1 to a conserved current. The B? No, out of not, no. The B, field B is this. I'm not building the B out of it. I have spin 1 fields. I have helicity plus 1 and minus 1. I use those to build my field B the way I showed last time. It has nothing to do with this. Okay, check it. It's an exercise for you. I know it because you can do it and you check. It's nothing deep. Okay, I'm giving you, so take this and check that this is the equation of motion for B and that this is what appears there. It's a well-defined problem for exercise, right? So I don't want to spend too much time here because I really want to get to other things, but I'm trying to show you that, so the takeaway is that you want to describe interactions of your spin 1 field with something else like the Higgs. You have to be careful. You have to do that through nodal currents because you have this equation del mu b mu nu equals something, right? And you're led to this, okay? Which has interactions of a particular type. Now this thing I have constructed, I have told you that you really just follow your nose and you're led to this somewhat complicated expression. We can actually write this or simplify this Lagrangian if we just make this definition, which, because you're very sophisticated, you know, is called the covariant derivative, but this is not really important. Let's just take this as a definition. So we put together, so what we call capital D mu acting on H is the normal partial, but we put here this term, and then again it's an exercise for you to check that this thing with this definition corresponds precisely to this more complicated thing. All right, so this is just cleaning up notation, if you like, but it leads to an interesting prescription which is worth noticing, which is called the minimal coupling prescription, which means that, so this Lagrangian here looks very similar to the first pieces I had here to begin with before I tried to do this couple the spin 1 to the Higgs, except that instead of partial derivatives I get this capital D mu, the covariant derivative. And so we can describe this careful procedure that I described for you. We can obtain the same answer by just closing our eyes and making this. Now I have included here a slide. Well, I will not go over this slide, but just make you aware that it is there to illustrate for you why this minimal coupling prescription works. In the sense that this is just something that you can follow rules, so I can tell you do that and you do it, right? But there are things going on behind the scenes, and there is physics going on behind the scenes, which is basically this, making sure that you couple your spin 1 fields to conserve currents. So it's there, you can take a look. Also, I'm going to skip this slide. You can read it later carefully, but what I'm doing here is now is I'm asking, okay, I showed you how it works for the U1 current. I have these other currents, the SU2 currents in the theory. So how do I go about coupling those to the Higgs in a way that leads to consistent equations? And basically, again, you can follow your nose and get to the answer. And at the end, I can summarize that answer by following this trick of defining an appropriate covariant derivative that will just reproduce all of that. So this is a very nice trick. So if you want to couple, so this was the term I had before that leads me to the couplings between B mu and the Higgs. I hope you can see here. So this is tau I, the Pauli matrices. Wi would be, I runs from 1 to 3. Those would be 3 other spin 1 fields. And by doing this, I am getting a theory where the W's interact with the Higgs, and everything is physically, it makes sense physically. Yes? Convention. So there, the taus are 1/2 the sigma, okay? And that's purely conventional. Okay, so now what will happen if you just insert this here is that, okay, you can expand and things will kind of explode. There will be many terms, okay? And you will find interactions, so let me focus on the ones involving the W's. As before, there are interactions between the spin 1 guy and 2 Higgses, like that, or 2 spin 1 guys and 2 Higgses. So that's very similar to the U1 case. But here there is something interesting. For instance, you will find couplings between a spin 1 guy and the upper and lower components of my Higgs doublet, the H+, which is upstairs, and the H0, which is downstairs. So there are W's that can convert one type of Higgs degrees of freedom to the other one, okay? And so this is pretty much what we mean when we say that the Higgs field is a doublet, okay? So there are things that can happen from one to the other. Now, so you see, until now, I have not mentioned anything about these local symmetries that you guys are in love with, but I have constructed the theory for you, and I'm claiming that you can get to this theory based on physical arguments, which are really physical arguments, okay? You won't, because they are related to degrees of freedom. But nevertheless, what you find, this thing, will have the following properties. It will be invariant under a transformation like this, which looks very much like the U1 we were dealing with before, but where we allow this parameter theta to be an arbitrary function of x, spacetime, okay? If at the same time you change your B mu in a way similar to what we were doing in QED by a derivative of that function. Notice also, I should have mentioned this before, so there is this G1 here. When I wrote this here, these terms here, there is a G1 and a G2 here, and this goes back to Freddy's lecture earlier, where he was asking how to allow helicity 1 particles interact, and through the argument at the end, he ended up with one arbitrary constant. He called it G, okay? So this is that. And there will be one G for the U1 and a different G for the SU2, okay? And that's really the only freedom that you have. So we call these coupling constants, the gauge coupling constants. And that appears here. But anyway, so it's a fact that this thing I've constructed here is invariant if you just do this carefully and you find it's invariant, okay? It is also invariant if I do something similar for the SU2. So this transformation, I make these theta i's, I allow them to be a function of x, provided I do something for the w's, which you can write. So it turns out that it's useful to write the 3 w's in this notation, where as a 2 times 2 matrix, it is w1 times tau1 plus w2 times tau2 plus 3, right? And in terms of that, this is how the transformation looks, such that your thing is invariant, okay? And again, I'm not going over the technical details because it's not really the point here, but it's an observation, and it's an interesting observation. So when I say that the important things are global symmetries and not these local symmetries, that doesn't mean that these things are not extremely useful, okay? It's a true observation anyway in this theory I have written down. So let's see, okay, we're going to use this in the next slide, but so I want to go back now to this issue of spontaneous symmetry breaking. Namely, we have this Higgs, which has this V here, which is non-zero, and I put the 4 degrees of freedom as I told you before, okay? So we just pointed out that this theory we have constructed is invariant when I make this transformation, the SU2 transformation. So I just take whatever field configuration f h of x and define a new one, obtained from this one by multiplication of this thing. And I ask you that you will have to check that this is indeed doesn't change your Lagrangian. But knowing that, you see there's something you can do. You can say, okay, if that's true, if this is invariant for, if you can make these changes and for arbitrary theta of x and things stay the same, I can choose the theta i's to coincide with minus the chi's that appear here, okay? Because this theta is allowed to be an arbitrary function of space-time, then for any configuration here I had here, which I could have been thinking of as a real fluctuation, I can choose that this way, and what that will imply is that the H prime field will contain no term. This will cancel, so this exponential will cancel that one. So this means that in this theory, you can decide to work with this guy, or you can equally well decide to work with this simpler guy, and it's the same physics, okay? So I will, of course, work with the simpler guy. Oh, what happened here? So there is an upshot here, which is, remember before I told you that these chi's would be the analogs of the spin waves. Well, now we're saying that really you may have thought they were there, but they are not actually, because this thing is working with this is the same as working with that. So the upshot here is this: the 3 spin wave modes that we thought could have been there, they are not there. They can be gauged away, we say. Okay. Now let me. So we have now introduced our spin 1 fields, know how to couple them to the Higgs sector, but the Higgs sector breaks, so has chosen some direction in field space, so it has this property of spontaneous symmetry breaking. So let's see what happens here, and let me illustrate that by focusing on the U1 current again for simplicity. So in particular, I'm setting just for simplicity here G2 equals 0 and keep only G1. And so I'm writing here the current, the one I wrote a few slides before, right? Had this form, these terms. And I can replace this form for H, right? So only something in the second component, which is V plus H. If you do that, you see that, okay, you're going to get little h's in different places, all right? So for instance, these terms that involve a derivative, they will always have to act on the little h. So these terms here are always dependent on little h. And these also have h-dependent terms, but this guy here has something else which is interesting. There is something that survives only from the v part, okay, which I have written here. I'm using here that qh is equals to 1/2 in my normalization. So that with these two, that leads to a factor of 1/2, the g1 squared, the v squared coming from here, the b mu, and then I'm not writing explicitly all the other terms which depend on little h, on the Higgs boson. I want to focus on this one for a moment. I've told you that the way that this current enters in the equation of motion for the corresponding U1 gauge field or spin 1 field is like this. It appears on the right-hand side of its equation of motion. But I have here the expression for that, one of the terms. So we see that by replacing the equation of motion for B mu looks like that. I have defined m1 squared as this coefficient here, and there are a number of nonlinear terms that depend on h that I have put on the right-hand side. What is important is that I see that this thing on the left-hand side, if I compare to the Klein-Gordon equation that we discussed a long time ago, right? This is playing the same role as the mass term in this free Klein-Gordon equation. And in fact, what we're seeing here is that now we are describing a system of spin 1 fields which have a non-zero mass, all right? M1 in this case. And this is coming about because of this non-vanishing expectation value V. So this is what is known as the Higgs mechanism, okay? So it's spontaneous breaking of the symmetry, which I insist is the global symmetry that matters, okay? And because you have coupled the Noether currents of that global symmetry to spin 1 fields, the effects is twofold. First, there are no analogs of the spin wave modes, and there is this massive guy, the spin 1, okay? So what? Okay, if you remember in our discussion of electrodynamics, we saw that the exchange of a massless spin 1 photon, like in a diagram like this, leads when you go to at lower in the non-relativistic limit, when you go back to configuration space, it leads to the Coulomb potential. Okay, so it makes a nice connection to things we know. This 1 over q squared is the propagator for the photon, but if now I do something similar, exchanging one of these massive spin 1 guys, I'm choosing here what we call the Z, it's something similar to this, but now we get a 1 over q squared minus the mass of that. And you can go through the same exercise, consider this in the non-relativistic limit where the spins of the electrons are not very important, do the inverse Fourier transform, and what you will find is that instead of just a Coulomb potential, it has an exponential here. It is so this potential is called a Yukawa potential. So we see that there are two different possibilities here. If you're exchanging a massless degree of freedom, spin 1 for instance, you get a long-range interaction like this. If you are exchanging instead something massive, you get a short-range interaction because this exponential, after distances which are somewhat larger than 1 over the mass of Z, or in other words, larger than the Compton wavelength of this object we are exchanging, they can become arbitrarily small. And this is, yeah, and I see you cannot, well, I don't know if you can see, I showed this picture before, which is a different process, alpha particles, but maybe you can see there are some rays here, they stop at some finite distance. Okay, so this illustrates what we mean by short range. But the range of these guys is much, much shorter, okay? It's, as we insisted before, we cannot see, so small that we cannot really see it. Now it turns out that when you turn on both G1 and G2, there is a linear combination of spin 1 fields that does not receive a mass, and that's connected to this particular transformation that doesn't change the direction of the vacuum. And that means that in the standard model, so having coupled these 3 W's and the B to the 4 currents of the SU2 cross U1, you're going to find that there is one massless spin 1 particle connected with this direction that kind of doesn't, it's not changing the direction of the vacuum, and 3 massive spin 1 fields. The massless one is what we call the photon. The other ones are the Z and a pair of charged particles that we call the W's, the charged W's. So we see that nature really hit this underlying symmetry quite well for us, okay? Basically, we had to wait until we could probe distances as short as 100 GeV inverse, which is roughly something like this, before we could really see and be sure that there was behind an SU2 cross U1 symmetry, okay? So we were not as lucky as the guy living inside a ferromagnet. This was not, it took a while, and it's because of this reason. Okay, the photon we saw easily very early on, but the rest was not so easy. Let me go on now to the, okay, so we have that, but now I want to focus on the Higgs boson. And so for this, let me try to do it in the following way. So let's recall, this is one of the terms that came from the currents. It's in the Lagrangian, so it's a term involving two Higgses and two Ws. And when the Higgses had a vacuum expectation value, that's what led to the non-zero mass for these spin-one fields, the quadratic term here for the spin-one fields. And this can be represented diagrammatically in this way. I'm putting, I don't know if you can see, I'm putting some crosses here to indicate a V, okay? V mu here stands for either W or Z. But we also have seen that actually in our Higgs field, V came always accompanied by H in this form, okay? These diagrams represent terms in my Lagrangian. So given that this is how this enters, I know that if I have this diagram, these kind of terms, I will have diagrams when I can replace this or this guy or both by an H. So there will be interactions between two spin-one fields, a single Higgs boson, and this will be just a VEV. Or also between two spin-one fields and two Higgs bosons. Turns out that this one here, the one with one Higgs and two spin-one fields, was particularly important for the Higgs boson discovery. And one thing to notice here is that its coupling is GV squared times V, and that is actually connected to the mass of these gauge bosons like this. Okay, so this coupling is fixed actually. So let me now I need to tell you one more thing about fermions, and I will use the template that I discussed yesterday. So we introduced these kind of terms for involving the Higgs and fermions like that. This will be invariant if this psi is an SU2 doublet, whereas chi here is an SU2 singlet, and they have U1 charges, Q psi and Q chi, such that they satisfy some relation with the Higgs charge. So I did this yesterday. It turns out that in the standard model, this kind of thing is actually what happens. And let me illustrate that by looking at the electron and its neutrino, the electron neutrino. The role of the psi here is, which I will call in this context L sub E, is something like this. The upper component is the neutrino, which is left-handed, and the lower component is the electron, also left-handed. Whereas the chi, the role of the chi here is being played by the right-handed electron. So we see these representations, this table, they don't give you all the information. There is a difference between the left and right-handed chiralities. And these are the charges, I'm calling them QL and QE, which we call hypercharges. Just to not get confused, these are not electric charges, but these are some conserved charges. So let me write this term now in terms of this notation, the L and the ER. And if I replace this H by, so 0 V plus H, I'm going to get something like this. Okay, so I have this, what came from H, and because this was in the lower component, the second component, this marries this ER with the second component in LE, which was EL. So I get a term like that, which I can write in the following way if I define ME like this coupling, which I'm calling now YE for the electron, times V. So this is what you get, okay? And we see that we recognize a mass term for the electron, and we also learned that the way that this mass term is arising within the standard model has something to do with the fact that the SU2 cross U1 symmetry is broken spontaneously. This ME is proportional to V. Okay, let me skip this comment because I'm saying that I'm running late. The most important lesson here for what I want to do next is that we also see that there is an interaction between the Higgs boson and two electrons, which goes like this. And we can read the coefficient, which tells me how strong this is. And it's something similar to what happened between the coupling of a single Higgs and two spin-one fields. It has something to do with the mass of in this case, the fermion. It's ME over V, okay? So what we have learned is that the origin of the masses of elementary particles, the ones that appear in that table, is related to the phenomenon of electroweak symmetry breaking. We call this spontaneous symmetry breaking of the SU2 cross U1 symmetry. In addition, there is a spin zero particle, the Higgs boson, this little h, that corresponds in some sense to fluctuations of the vacuum, okay? Fluctuations in the difficult direction, the massive direction. We also learned that the couplings of the Higgs boson to other particles are basically determined by the mass of those other particles. They are proportional to the mass of those particles, or in the case of spin 1 fields, to the square of the mass. Now, I mentioned before that within the standard model proposal, this is the Higgs expression for the Higgs mass. We didn't know lambda, and this is why before we discovered the Higgs boson, we really didn't know what its mass was. We didn't know where to look exactly, okay? But we knew how to look, because we knew how it couples to other things. Now in this, so I could spend a full lecture talking about these things. I will only mention a couple of properties. So what I'm showing here is the following. This is information about what we call branching fractions. So remember what I mentioned, I think, in the second lecture. The Higgs boson lives a very short lifetime, right? It decays very fast. It decays into things. So it's very important to know into what it decays, because those are the things that we are really going to see in a detector. So this plot here has to do with that information. How does the Higgs decay? And it can decay in many different ways, and how it decays depends on what it is, its mass. So for example, before we knew where the Higgs was, if it had been somewhat heavy on this side of the plot, it would have decayed most of the time. So this is the fraction between 0 and 1, most of the time into a pair of W's, next into Z's, and then smaller decays into other channels. And so you see that how this is it has a fairly non-trivial dependence on the Higgs mass. For the Higgs mass, we know it is now, which is 125 GeV. I have put for you here the numbers, but so it is on this line. We see that the most important decay is actually into pair of bottom quarks. Okay. The next one, so it's about 60% decays like that. The next one is into W's, some 20%. Then there are other decays into pair of gluons, taus, cis, pair of photons, okay, muons down here. And these things are pretty much controlled by the mass of the objects they are decaying into, okay? So we knew, once we knew the mass, we knew how to look for these things, what to expect. Now you might say, but wait, what do you mean that the Higgs can decay into gluons, for instance? First of all, gluons are massless, and I have told you their couplings to things are proportional to mass, so this sounds strange. Furthermore, the Higgs doesn't carry the color charge. Why should it interact with gluons? But it turns out it does, and it can do, so this is a genuine quantum effect, okay, and proceeds as follows. And so even though we have not talked much about gluons, it's remarkable that they end up playing an important role in Higgs physics. And it's like this. The Higgs, we know couples, for instance, to a top quark. But the top quark can appear in a loop, and because it carries a color, it can couple to gluons like this. So this leads to an effective coupling between two gluons and the Higgs. And we can estimate the size of this. Actually, okay, so it goes like this. There is a price you pay which is very similar and related to the phase space price I discussed a couple of classes ago. The loop costs you a 1/16 pi squared. There are couplings, Y top that enters at this vertex, and G3 will be the QCD coupling that enters at each of these vertices. So there are two of those. It turns out, and maybe if you want to know, I can tell you later, that this loop, I'm not only going to do dimension analysis here. This loop goes like 1 over the top mass squared, the thing that is propagating here. So look at that loop, and it has to go like 1 over mass, and it's that one, okay? So if I'm going to define an effective dimensionless coupling between GG and H, glue and H, these guys are dimensionless. I have one over empty here, so I need some other scale here. The natural one that appears is the mass of the Higgs mass itself. These two masses are not too different. The Higgs mass is 125, the top mass is 170, okay? These couplings also turn out to be order 1, but you have this 1 over 16 pi squared. So you can estimate this effective coupling to be something relatively small, like this. Now, the reason I'm telling you this is because I want to compare to the main decay mode of the Higgs, which I told you was into BB bar. I also told you that that coupling was proportional to the bottom mass. In this case, it's mb over v. And do you remember what was the bottom mass? 5 GeV, roughly. Put here for other reasons, but I cannot explain, but okay. So this is 4 over 174, and numerically this is also a small number, 2 times 10 to the minus 2. It's bigger than this one, but only bigger by a factor of a few, okay? So it turns out that this loop-suppressed coupling can be comparable to this one, which is the dominant one, and that's what we're seeing in that plot. Remember, I also mentioned the second class again, the question about why the Higgs width was small. It was 4 MeV. I also showed it so here, 4 MeV, which is smaller than you would have guessed purely based on dimension analysis and phase space. And that's connected to the fact that this coupling is small, okay? So at the end, it's just the smallness of the bottom mass compared to the electroweak scale V. But actually, this coupling, this glue-glue Higgs coupling, the most important aspect of that is not to induce a decay of the Higgs. The most important aspect is that it plays a role in the production of the Higgs, because if you're going to see the Higgs decaying, you first have to produce that. So basically, we're reading the diagram in the opposite direction, but it's the same diagram. Now, I also showed you before that there are couplings to photons, which are also very important, turns out. They proceed in a similar manner through loops of, in this case, electrically charged particles, like the top or the W, the charged Ws. These are a very small branching fraction, like 0.2%, okay? But they turn out to be quite important at the LHC because seeing photons is a relatively clean signature. So this was the discovery of the Higgs boson in the data shown in 2012. And so the one, let me briefly say, so the one on the left-hand side, what they're looking for is, so I'm showing you this diagram so you have some idea. You produced the Higgs through gluons. We call this gluon fusion, and it decayed into a pair of photons. What you're plotting here on the horizontal axis is called the invariant mass of the final state, the photons that you actually see. That means you measure the 4 momenta of the 2 photons, sum those 4 momenta, square, that's what we call the invariant mass. By momentum conservation, that must be equal to the momentum of this guy here. So it must have something to do with the Higgs mass. And this little bump here is that, okay? That's the Higgs in this channel. It was also, this was the other golden mode, where the Higgs is produced more or less in the same way, but now decays into Z's. The Z's are again relatively heavy, so this coupling is not negligible, and the Z's then decay into leptons, okay? And that looks like this. It's this larger bump. And you can ask me what are the other peaks later, but maybe let me move on. So you can now go over the exercise. So these are actual events that are Higgs candidates. This will be 2 photons, more or less following the rules that we discussed last time. This will be a ZZ, a candidate for ZZ going into 2 muons, which is this red and this red, and 2 electrons, which are these 2 green guys. So these are candidate Higgs events from CMS. I want to emphasize one more thing, which is that we have really discovered a new type, a qualitatively new type of interaction with this Higgs boson discovery. It is an interaction. These are vertices that are proportional to the mass of the particles involved. And this is completely different from all the interactions we had before, which were always of the gauge type of interactions, which are characterized by a single coupling G, right? So they are universal. The gauge interactions are universal. These ones are not. And these are experimental data. Basically, it's a plot of the strength of interaction to different particles, the top, the strongest one because it's the heaviest, the Z, W, bottom, tau, as a function of the mass of the corresponding particle. And we see this beautiful confirmation, if you like, that the strength of these interactions are proportional to the mass of the particle involved. So let me summarize what we have achieved here, which is that, so first of all, really this Higgs boson discovery can be seen as a culmination of a process that involves both experiment and theory. It's really a success. One thing that is interesting to appreciate is that the standard model of particle physics, that table that I have shown you, actually describes something like 100 degrees of freedom. So it's a bit deceptive, that table, okay? There are many degrees of freedom there, but many of those are related to each other by a number of symmetries, okay? So symmetries play an important role. We are, by this establishing this is telling something to us about the structure of the Lagrangian. I focus here on the symmetries whose nodal currents are coupled to spin-1 fields. In particular, what is the electroweak sector? I said very little about QCD. We found that, interestingly, the vacuum of our world has chosen a particular direction in this internal symmetry space. And one consequence of that is that some of the spin-1 degrees of freedom are massive and therefore mediate short-range interactions. So as I already emphasized, this made it quite non-trivial to realize and establish what was really going on. And this is really a journey that started a long time ago with the discovery of radioactivity in 1896. Okay, so this just to put into perspective that we have kind of reached an important milestone. We also saw the following, that the non-particles, the non-elementary particles, owe their non-vanishing masses to the phenomenon of electroweak symmetry breaking. And here I have to make an important remark, which is that when I make this statement, I am recognizing that things like the proton or the neutron, which are the things of which we are made mostly, are composite things, okay? They are bound states, actually complicated bound states of quarks and gluons, and actually the mass of protons and neutrons, which is really your mass, okay? That has very little to do with what I'm telling you about here, with electroweak symmetry breaking, okay? And we have understood that part for a long time. I haven't told you here how this works, but what we know is that only a small part of the mass of the things we are made of arises from the quark masses, for example. However, this small electroweak symmetry breaking contribution is quite important, and things would be very different if it wasn't there. For example, if the up and down quarks, which are inside protons and neutrons, were massless, let's say they didn't couple to the Higgs, okay, then the proton would be heavier than the neutron, because there will be no distinction between up and down, so you would think they have the same mass, but actually there is the proton is electrically charged, and so electromagnetism gives a bit of a contribution to its mass and makes it heavier than the neutron. As a result, it would decay in this way, and that would not be very pleasant for us, okay? So we would not live very long. Also, the electron mass, which of course is an essential part of us, it's in atoms, even though it has a small mass of the whole thing. So this is tiny compared to other elementary particle masses, but if it was not there, if it was zero, the electrons would be relativistic, right? It would be very different, okay? So our world really would be very different if this phenomenon was not there. Now I think I know I'm negative how much, because, okay, so I have, okay, let's take this as part of the discussion, because I think it will generate discussion. So I focused here on one particular aspect, right, of the standard model, this spontaneous symmetry breaking, how this works, why the Higgs boson discovery finished telling us some story about that. But there is a wider context, and I'm giving you here 3 examples, just to illustrate that this knowledge that we have gained trying to understand this very microscopic physics can help us to understand things that are maybe, so they're completely different systems. So one example I'm going to give you is, so we can understand something about how stars like our sun works, okay? And there is something called the standard solar model, complicated thing. And don't ask me about that because I don't know, but it's for sure, an important ingredient of that is based on all these interactions that we are discussing and that we have been studying for a long time. What is interesting is that actually this understanding how this the sun works played an important role in understanding the properties of neutrinos. I also didn't say much about neutrinos here, but in that sense kind of closes a loop. Your understanding of particle physics allows you to understand something about the sun, which in turn gives you information that allows you to understand something about particle physics. One more example, supernova. We know that they play an important role in, let's say, structure formation, or in how galaxies, how this works. And so there are many things that we still don't understand about supernovae, but we can ask concrete questions based on our microscopic knowledge. Okay. The early universe also. It has been mentioned before here that an early epoch that we call Big Bang nucleosynthesis, which is a time where nuclei were synthesized, hydrogen, helium, and small traces of other elements. And in fact, the way that the reason we can contemplate answering the question of how this happened is directly based on on this knowledge of the microscopic physics. And in fact, so you can make predictions and compare two observations of a different nature, and the success is such that actually we think we understand quite well what happened to the universe down to times as early as the epoch of BBN, which was around, so in, it was the first couple of minutes of the life of the universe, okay? So we can ask these questions about the past based on the knowledge we have. So these are examples that illustrate how a solid understanding of the very small can illuminate questions about the very large or the very early, and vice versa. And so this is to tell you that in recent times, there is this interesting situation where different fields that deal with the very small and the very large, there is a very non-trivial interplay that allows to learn together. There are also open questions, and maybe this is where there can be some discussion if you like more questions. Maybe let me, so there are some questions still about the Higgs sector. I will skip this one and go to the next one, which is the last one. I have told you that we have some understanding of how the elementary fermion masses arise. They arise because these fermions interact through Yukawa interactions with this Higgs field that is getting a non-zero vacuum expectation value. That proceeds through a coupling, a Yukawa coupling. We don't know exactly what sets the value of those Yukawa couplings, which means that we don't really can answer why the masses of the fermions we see take the values they have. Also, we see that the fermions have widely different masses, hierarchical. Okay, the top mass is about 170 GeV, right? The electron is much lighter, 0.5 MeV, and there are things in between. The neutrinos much lighter. So there are questions that are open questions, and perhaps this is one of the possibilities that these things we see, these patterns, are a manifestation of further symmetry principles that are at present hidden to us. The neutrino masses, which are tiny, may be providing a glimpse into physics that operates at much higher scales. We don't know this. There is also the issue of dark matter that I haven't mentioned here, but all this beautiful table that we have, we know now, is describes the matter which composes only a small part of the total matter in the universe, like 4% of the energy budget of the universe. So what is dark matter and how does it fit with the rest of the standard model? It's an open question. We also see that in our universe, it's basically dominated by matter. There are only very tiny traces of antimatter. And this is a question that actually we don't know how it came about. There are ideas. It must have happened. So why we ended up with more of one type than the other must correspond to processes that happened very early in the universe. We don't know exactly when or how. And so that's one of the important open questions. You can also mention other things, again from cosmology, inflation. There are other ideas that we have reason to believe happened, and you can ask whether there is any connection between those ideas and particle physics. So these are examples, besides being a list of things that are at this point open, it's also to illustrate that we can formulate fairly deep questions in a fairly precise way, and we can do that because we know a lot about particle physics in particular, okay? And as I say here, there are no lack of ideas to address these questions and other. But of course, to make concrete progress, we will require some sort of experimental or observational input, okay? Only then we will know whether someone's idea or another one's is really what happens in the world. So I don't know, perhaps you will be part of that story. And I stop here.
Okay. In one of these slides, you said that you constructed a state of left-handed fermions and right-handed fermions, but you, in the right-handed, you didn't put the neutrino. So I inferred that the neutrino is only left-handed. So why is that? And how do we
don't know? So one thing I've told you is that the degrees of freedom that are there, we cannot derive from just sitting down and thinking what are the degrees of freedom that are out there in nature, okay? So it's something that you have to go and find out, and this observation that you are making, which I forgot where I put it here, is a statement that we have not seen a right-handed neutrino, okay? It doesn't mean that it cannot be there. In fact, there are many models where you can put a neutrino and its properties are naturally such that it would be very difficult to see it. So it would be no surprise that we have not seen it. The day we see something like that, we will add it to our table of that summarizes degrees of freedom, and we will try to describe that in some Lagrangian. But it's as simple as that. I mean, there are no
what is the smallest scale? I think that is the scale set up by the Higgs mass. No, like
what is the smallest scale? What?
Yeah, what set up the typical scale where everything shows up and all symmetries start to be shows up is the scale of the Higgs mass. No.
So there is no, let's say, precise value where this happens. It's a continuous thing, but so it's what the scale we call the electroweak scale. So think of that as 100 GeV, roughly. Okay. Now we started, so in the 1980s, we produced the Z and W, we saw that, and we started exploring their properties. So it happened, so they have mass 80 and 90 GeV, somewhat below that. But by exploring the properties, that's where we learned actually that, and we got convinced that even before seeing the Higgs, what you have behind, there is really an SU2 cross U1 symmetry, and it is spontaneously broken. This we knew, and we measure V. So okay, when you explore roughly that scale, a scale we are still exploring. So that's one of the main goals of the LHC, is to really try to understand what's happening at this scale in full. That's what we call the electroweak scale.
Yeah. So my thing is that if you have if in the standard model we have a scale, we always facing a problem because we have a lot of quantum fluctuations come from a very small scales, like in a critical state of a Ising model, for example, can show like the nature would be adjusted in a very close to a critical phase. Like this is not unlikely. Like
yes. Okay. So
like a full theory do not can't be quantum field theory, or well, like a relevant quantum field theory, a quantum field theory that has a mass term, like something like that, quadratic, that that set up on a scale and say, oh, this is where things occurs, like correlation length. So
you are quite right that in the Higgs sector of the Standard Model, what's happening is exactly what you're describing. So if people have seen these things, they will understand. If they don't, they will not understand zero of what you're saying.
Yeah,
But indeed, so the scale is there because we have measured it, right? Then there's a question of whether you have to tune things to be that scale. And that's actually, we don't know what's the answer to that. We don't know if for some reason the universe is tuned, or as most or many people would believe, there is some sort of mechanism behind. So there is a good analogy in superconductivity between comparing a Landau-Ginzburg description versus BCS. Perhaps there is some additional microscopic dynamics that could explain that. Maybe it can explain dynamically why the electroweak scale is broken versus not, which right now it's an observation which we know how to put into the Lagrangian. We know how to parameterize that into the Lagrangian. But those are precisely open questions. So that's part of what I mean when I say that we are exploring the electroweak scale and we want to explore it fully. We don't know if we're going to find the answers to those questions, but many of us would like to understand those issues better.
So how close LHC is to probe new physics, like to find this new mechanism that theorists, I think that the theorists have some ideas about the mechanisms, no?
Okay, exactly. So it depends on what are the theorist ideas, right? So there is no, when you're exploring the frontier in energy, right, places we have never explored before, you cannot really know for sure what or when you're going to find something. That's part of the business. Now, within some theories, you can try to have some expectations, right?
Okay.
Now, it turns out that we know so much about, so I told you some story here, but we have measured many things precisely about properties of particles and so on, sensitive to loop level effects, that if there is new physics, those very precisely measured quantities would be affected by the new physics. And that leads you to think that if there is new physics, it will have to be some physics that we call of a decoupling type, meaning that if you make it heavier, the effects, which are small but on very precisely measured quantities, becomes smaller, okay? And it's not difficult you don't have to struggle to write down theories like that. It's natural. But those are the kinds of, so when you think about proposals for physics beyond the Standard Model, they normally have that property. So that means also that if things are heavier than you thought, things become harder to find. And it may be that perhaps there is something out there and could be outside the reach of the LHC. That's a logical possibility. Again, we cannot, we don't know that's there.
Okay, we are already running late. Let's thank Eduardo again.